Hi, welcome to our 18th lecture of Graduate Combinatorics. Today we'll continue discussing enumeration under group action. In the previous two lectures, we prove the statements 1, 2, 3 listed on the page there. So let's briefly go over them. So assume we have a group that's acting on a finite set X. Then the first result states that the orbit of an element X equals the index of the stabilizer subgroup of that element X in the group G, which is the same thing if the group is finite, is the ratio between the cardinality of the group and the cardinality of the stabilizer. So this is usually called the orbit stabilizer lemma or orbit stabilizer theorem, and it's a very, very important result in this area. Now, the second result states that the number of elements in X equals the cardinality of fix of G, which is the number of points of X that are fixed by every element of G, plus the summation over all of the elements X whose stabilizer is not equal to the group itself of the index of Gx in G. And this result too follows from the observation that the binary relation X is equivalent to Y if and only if there exists an element G that sends that acts on X and produces Y, is an equivalence relation, and this equivalence relation produces equivalence classes, and the result too follows from stating that the cardinality of X equals the sum of the cardinalities of these equivalence classes. And in the case of a group acting on itself by conjugation, so when X is G and the action is conjugation, we obtain, as a consequence of 2, we obtain the result 3, which states that the cardinality of the group equals the cardinality of its center. The center consists of all the elements that commute with every element of the group, plus the summation over all X in G, or X not in the center of the index of the centralizer of X in G. The centralizer of X consists of all the elements G that commute with X. Okay, so this is commonly known as a class equation. So in the previous lecture, we gave some applications of this result. The main result of today's lecture is what is called Burnside's lemma, which is stated a little bit crammed at the bottom of the page, but I'll expand it on the next page. And it answers this natural question. When we have this group action of a finite group on a finite set, we are interested in what is the number of orbits of this action. So orbit stabilizer lemma gives us a formula for the cardinality of a given orbit, but this Bonsai Lemma will give us the answer to the number of orbits. Now, there's a bit of history about Bonsai Lemma. This lemma was known to Frobenius, I think, before Burnside. So it's a bit of a wrong attribution here. But anyway, this is a name that this result is known now in mathematics. So the result is the following. As before, we have this group G acting on a finite set X. And for an element G of the group, we define fix of G as the collection of points from X, elements of X, that are fixed by this group element G. And Bonsai Lemma states that the number of orbits equals the average number of fixed points, which equals this expression over there. It's 1 over G, 1 over the cardinality of the group, times the summation of overall G in G of the cardinality of fix of G. So it's the average of this fix of G, cardinality of fix of G over all G in G. Okay. So let's take it here again. So Bernstein lemma, G acting on X, fix of G, the set of points fixed by G, and then the number of orbits, maybe the easiest way to remember it is in words, the number of orbits of the action equals the average number of fixed points, which can be represented as this summation. Now, how do you prove this result? Well, what we to do is we'll do a double counting. So consider the following set, the set of order pairs of the following form. Gx, where G comes from G, X comes from the set X, and G acting on X is X. So all the order pairs where G acting on X, G fixes X, okay? Now, we want to count the number of such order pairs. And now you can think of order pairs as essentially as a matrix in which maybe the rows are indexed by the first coordinate and the columns are indexed by the second coordinate. So when you're counting these order pairs, you can start with whatever coordinate you like and do the counting in that order, and the result at the end should be the same. So if we start with the first coordinate, the cardinality of the previous set is what? Well, we pick an element G in G, and for each such element G, how many x's do we have such that G of x equals x? Well, this is exactly the cardinality of this set fix of G. Okay, from the definition. So fix of G contains all the element x that are fixed by G. Okay, so that's good. So we get one formula, but now we can do the same thing. If we start a count with the second coordinate, we get the following cardinality. Now, in this case, we start with x, so we have an element x in x, and we're counting all for each such x. We are going to count all the elements G such that that fix that element x. So it's going to be a summation over all x in x, the cardinality of the stabilizer group Gx. Okay, and so these two things must be equal. So let's do that on the next page. So we have that the summation over all G in G, cardinality of fix of G, equals the summation over all x in x of the cardinality of G of x. So far, the number of orbits hasn't made an appearance, but apart from the equation has made an appearance, which is the left-hand side. So let's work on the right-hand side a little bit. Now, we know from the orbit stabilizer lemma that the cardinality of the stabilizer equals the ratio between the cardinality of G and the cardinality of the orbit of X. And so from here, what we get is if we rewrite both sides, we are going to get summation over all G in G of fix G. We take the cardinality of G as a common factor and we multiply it by the summation of all X in X of 1 over the orbit of X. And now if you want to be, you can move the G on the other side. So we have that the average number of fixed points equals the summation over all elements in X of 1 over the cardinality of the orbit of X. And now here, this doesn't look like the number of orbits, but you can look at it in a different way at this summation on the right-hand side. So I'll write it here at the bottom. So the set X gets partitioned into the orbits of various elements. So the orbit x1, let's say orbit x2, let's say they are like k orbits, so orbit xk. Okay, so let's say k is the number of orbits. Okay, now let's say each of these orbits, let's say orbit of element x1 is the set consisting of alpha 1, alpha r. So x1 is one of them. So we just took a representative. Orbit of x2 is beta 1, beta s, let's say, and so on. And orbit of xk is gamma 1, gamma, let's say, t. Okay. Now, when we do this summation on the right, so I'll continue here, the summation over all x in x. The summation over all x in x splits according to each of these orbits. So it's going to be a summation over all, let's say, j going 1 to k of the summation over an element, let's call it y, in the orbit of xj of 1 over the cardinality of the orbit of y, but because y is in the orbit of xj, the orbit of y is the same as the orbit of xj. Okay, so that's a useful property there. And then this is going to be a summation of j equals 1 to k. So we're summing, if you pick an orbit, let's say we pick the first orbit of x1, and you're summing over every element of that orbit, you're summing 1 over the cardinality of that orbit. So for each element here, we're summing 1 over r. So we have 1 over r plus 1 over r. So when you sum up, you get a 1. Similarly, if we did the same thing, so that we get the 1 contribution from the orbit of x1. If we take j equals 2 and we sum up over every beta 1 to beta s in the orbit of x2, we're summing up 1 over the cardinality of the orbit of x2, which is 1 over s plus 1 over s times. So we get again a 1. We have a 1 there, a 1 there, and so on. So the main point here is that this expression here, this equals 1 for every j. And so we're summing up at the end, we are going to end up with a summation from j equals 1 to k of 1, which is k, which was defined as the number of orbits. And that finishes our proof. So there's a bit of subtlety here at the end when you have to transition from this sum over all x in x of 1 over the cardinality of the orbit of x to look at it in a different way using this partition of x into orbits, and it turns out that you end up with the number of orbits after you do this calculation. So yeah, so if you want to have a quick reminder of the proof of Bonsai Lemma, is essentially double counting. So you count order pairs g and x such that g fixes x. So let's do some applications now. Well, first, let me give you a quick corollary. If we use this result, if we apply it to the action of g on itself via conjugation, we get that the number of orbits under this action, which are called the number of conjugacy classes, of g equals the average number of fixed points, and in this case, the average number of fixed points is the summation. It's the average 1 over g over all g, and the fix of g gets replaced by cg, where I'll recall here, where c of g is the centralizer of g consists of all the group elements such that g and x commute. So this is just an immediate corollary from the previous result. Now let's do some applications of this result. So I'll give the first application. It's a very common question on candidacy exams, or sometimes even on prelims exam in algebra. So this is a result which is due to Camille Jordan from 1872. And I require the following notion. So it's a notion of a transitive. So let's say G acts on a set X. We say that this action is transitive if for any x and y in X, there exists G in G such that G maps X to Y. So let me put it here in kind of more only X and Y in X, there exists G in G, G acting on X equals Y. Okay. So all the elements of X look alike via this action. That's kind of what informally it says. And now, so this is the definition. What is the result that we're trying to prove? So let G be a group acting on a set X if cardinality of G is greater or equal to 2, cardinality of X. So if this action is non-trivial, so the group consists of at least 2 elements, the set consists of at least 2 elements, and this action is transitive, then there exists a derangement. So what is a derangement here? There exists G in G such that G doesn't fix any point. So G acting on X is different from X for any X in X. Okay. Now there's a lot here. So again, transitive for any 2 points, there is a group element that maps one into the other. And then, so you have this kind of nice action, this transitive action, and the result is that in that case, there exists some group element that doesn't fix any point. Now, what does it have to do with Bonsai Lemma? Well, you can interpret the action being transitive. So let's say G acts transitively on X. That is equivalent to what? Well, it means that for any X and Y, Y is in the orbit of X. So Y and X are equivalent. So that means that there's exactly one orbit. So the number of orbits is 1, which is the same thing as orbit of X equals X for any X in X. Or you can say there exists an element X such that orbit of X is the whole set. They're all equivalent. Okay, so now the number of orbits appears in Burnside lemma. So by Burnside lemma, 1, which is the number of orbits, equals the average number of fixed points, which is, let's write it, so it's the average over all G summation over all G in G of fix, cardinality of fix of G. Now, cardinality of fix of G is an integer and is greater or equal to 0. So you have an average of this of these non-negative integers equals 1. And what else do we know? Well, we have the following. There's one element, which is the identity element of G, that fixes everything. So the cardinality of this is the same as the cardinality of X, which is greater or equal to 2. So we have here, we have an average of non-negative integers that equals 1. So one of these cardinalities of fix of G has to be greater or equal to 1, and one has to be less than or equal to 1. I mean, theoretically speaking, all of them could equal 1, in which case, you know, we are still good. However, we have this element, 1 of G, where fix of where the cardinality of this fix, it's fixed, is greater or equal to 2, which is bigger than the average. So if you put this together, that means that there exists an element G where the cardinality of x of g has to be strictly less than 1, but this cardinality is non-negative, so that means this element, the cardinality of its x is 0, so that means that this is equivalent actually, that g of x doesn't equal x for any x in x. So that's this result of Jordan. Okay. All right, so let's do some other examples. So let's go back to one of the examples that we stated at the beginning. So let's say we're looking at the number of colorings of the edges of a regular tetrahedron that are invariant under rotational symmetry. So the number of colorings, let's say we had 3 colors then, but let's say in general lambda colors. Okay. So we have, let's draw a picture here. Say this is a regular tetrahedron. And let's note its corners A, B, C, D. So you can take it, play with it, rotate it, and so on. And, you know, see if when you put it back, what permutations do you get on the vertex set of A, B, C, D. So if we have, if we didn't have this condition here, you know, invariant under rotational symmetry, if that, you know, if we ignore, so if we ignore these rotational symmetries, you have 6 edges. So you know, you have 6 edges, and each of them can get lambda colors, so you get lambda to the 6 colorings. So lambda equals 2, you get 64. Lambda equals 3, you get 3 to the 6, 729. Okay, but now we are not going to ignore the symmetry. So 2 colorings are going to be the same if you can, if you rotate the tetrahedron, you get 1 coloring from the other. So I think we had an example before with 5 edges colored 1 color and 1 edge colored a different color. So let me see where that is. Here. So in lecture 16, we had this example of if you have 5 edges colored purple and 1 edge golden, all these colorings are essentially the same. These are not going to, these 3 colorings that you see there are not going to count as different colorings because you can rotate the tetrahedron, the first tetrahedron, to actually get it in the second position. So if you want to go from here to here, for example, you can take the segment that joins the midpoint of this edge and the midpoint of the golden edge, and you can rotate, you know, respect to that segment 180 degrees, and you can get well. Let me see. Yeah, and you can get that that one. You can get from here to here, for example, by looking at this face that's on the kind of on the right side, and so you can rotate this face this way, counterclockwise, and you can get the other coloring. Okay, so the first thing we have to understand here is what can we say? Let's say G is the group of rotational symmetries of the tetrahedron. Okay, so what can we say about it? And there are different ways to figure out this group. First, let's figure out the order of it. So one way to figure out the order is to remember the orbit stabilizer lemma. So the cardinality of G will be the, let's say, the cardinality of the stabilizer of A n times the cardinality of the orbit of A. So cardinality of the stabilizer of A is what are the rotational symmetries that fix the point A. And let's look here, G of A, what the permutation does it consist of? Well, first of all, it's going to have the identity, because that fixes everything. But then you could if you fix A, then B, C, D, essentially they're going to rotate. And how many rotations can you have there? Well, you can rotate if you go to the, let's say, if we go counter clockwise, so that will be B goes to C, C goes to D, and D goes to B. Or you can rotate the other way around, and that will be B goes to D, D goes to C, and C goes to B. So those are the only rotational symmetries that fix A. So cardinality of G of A is 3. And intuitively, it's pretty clear that all the vertices are the same, A, B, C, D. So the orbit of A consists of all the, I can rotate this this tetrahedron so that at the top, any vertex can arrive at the top. So the cardinality of, so the orbit of A consists of all A, B, C, D. So this is a transitive action. So in this case, we get that the group has 12 elements. Now, what are the elements of this group? Let me draw the picture again. A, B, C, D. And G is the group. Of the tetrahedron. And if you want to figure out all the symmetries, one way to do it is you can look at each order pair. Let's say you pick an order pair AB, and this essentially can be mapped to any by rotation to any other order pair. Well, how many other order pairs do we have? Well, we have 6 edges, and each of them has two orderings, so there are 12 choices. So AB could be mapped to AB. In that case, C and D will be fixed because that means that A gets mapped to A, B gets mapped to B. So the only way that you fix this to elements means that C and D have to be fixed. So you get the identity permutation. Let's see what happens if we map AB to BA, for example. In that case, we map A to B and B to A, and that automatically forces that C gets mapped to D and D gets mapped to C, and we get another permutation, which is the product of these transpositions, AB times CD, which is not the one from before. And similarly, you can do that for every pair of edge. So there are 12 ordered pairs. But what you end up is that G will consist of the following group elements. So we'll have identity. Then we have the ones as before, B, C, D, and B, D, C. This together form that stabilizer of A. And you have similarly a stabilizer of B, which would be A, C, D, and A, D, C. This is G of B. And then if you want to do G of C, you can do A, B, D, and A, D, B. So I mean, G of A minus the identity in each case. So, okay, so let's give fix C, and then we have A, B, C, and A, C, B. This one fix D, they're in, along with the identity in the stabilizer D. And then we have these other permutations, which swap these pairs of vertices AB with CD. So AB with CD, it's again, if you look at this, take the midpoint here and take the midpoint here, and you do a rotation along this of 180 degrees, then if you rotate, let's say this way, then A is going to end up in the place of B, B is going to end up in the place of A, and the C and D also swap places. So and that will happen for any two opposite edges. So AD and product BC. So this is the group of symmetries, and it has, so we have now, so we have identity, which has order 1. So this has order 1. Then all these 8 3 cycles, so they have order 3. And then you have these 3 elements of order 2. They're involutions, product of 2 disjoint transpositions. Okay, so this is the group, and what this group does, it acts on the edges of this, it acts on the vertices, but it also acts on the edges of the, so what we do here can be applied to problems of coloring of the vertices of the tetrahedron. And so in this situation, what is our set? So what the set X, so for us, the set X consists of the set of lambda of let's say colorings with lambda colors, the set of colorings of the edges of the sides of the tetrahedron with lambda colors. Okay, so it can be like a set of functions from you know, A, B, A, C, A, D, B, C, B, D, C, D to the set 1, 2, 3 lambda. This is it. And G acts on it. We'll discuss more about it a bit later. But for now, I think things should be clear. And what we want to do is we want to figure out the number of orbits of this action. So the number of colorings invariant under is the number of orbits. And by Bonsai Lemma, what is this number of colorings? This is the so number of orbits will equal 1 over the cardinality of the group, summation over all G in G, the cardinality of fix of G. So here we're going to count those colorings that are invariant under these various elements of G. So let's start with the G is the identity. Then in this case, every coloring is essentially fixed by G, because yeah, identity fixes everything. So in that case, uh, fix of G will consist of all these possible colorings. So it will be X, and now cardinality of fix of G will be lambda to the power 6, because every edge can be colored with lambda colors. Okay. Now let's take another example. So for this one, let's do a picture. So the non-identity elements of the group have two forms. So either you have a cycle of length 3, or the product of two disjoint transpositions. So let's say we take the group element G. G is, let's say, B, C, D. So it's the one that goes counterclockwise this way. Okay. Now, what colorings? What is the cardinality of what? First of all, what would be fix of G? So that will be colorings that are invariant under this operation. So if you're invariant, it means that this edge AB, edge AC, and edge AD, they have to have the same color, and the edges at the bottom, when you rotate, you have to get invariant, so they have to have the same color. So that's how a fix of G looks like, and therefore the cardinality of fix of G will be, you have two colors that you're using there, and you can pick them in arbitrary number of ways, so it's lambda squared. Okay, so that's in that situation. What happens? So that will be the number of colorings for every time G is a 3 cycle. So that's not hard to see. Let's draw the picture. So A, B, C, D. And let's say we have the other one. That's, well, let's take G in this case, the one that swaps A with B and C with D. Okay. So now, so again, what does this permutation do? So the AJB and the HCD, they stay the same under this permutation. But what happens is that BC, it can be mapped to AD, so they could get this. You want the colorings that these two edges get the same color, and similarly BD and AC get the same color, but the remaining two, like AB, could get the color on CD could be it's not golden. It's independent of that color. So here you could get let's say a purple. So that's how the set of colorings that is fixed by this permutation looks like. This is how a fix of G looks like, and therefore the cardinality of fix of G in this case, fix of G, will be lambda to the 4, because you have lambda choices for AB, lambda choices for CD, lambda choices for AC and BD, which have the same color, and lambda choices for AD and BC. Okay, so when you put them all together, when you plug in all these cardinalities of fix into that formula, what we end up with is the following. We get that the number of colorings of the sides of the tetrahedron with lambda colors is 1 over cardinality of G. Sorry, let me just write again, summation of G fix of G. And this equals, that's 1 over 12 And now identity gave us lambda to the power 6. Each cycle of length 3 gave us lambda square, and there were 8 of them. And then we have 3 of the other ones, and we get 3 times lambda to the 4. Okay, you can rearrange them as you want according to their powers. That's fine. Just a quick observation: when lambda equals 2, if you had no restriction, remember 2 to the 6 was 64. In this case, when you do the calculation, I think you end up with 12 here. And lambda equals 3, if 3 to the 6 was 729, and if you do the calculations here, I think the result is 87. So there are much fewer under this rotational symmetries. Okay. All right. So I hope that was clear. Let's do another example now. Let's count necklaces. So let's say we want to count of necklaces using n beads, number of necklaces having n beads, where each bead can have lambda colors. Okay. So again, if we have no restrictions, then this number, so no restrictions, this is lambda to the n. But what we want to count the ones that are invariant under, let's say, circular symmetry. So how many of such? So let's do some. Let's do a specific example. So let's say n equals 6 and lambda equals 2. So let's say I'm using blue and gold. So in that situation, I could have this one uses all blue. Okay, I can use one gold here and blue everywhere. And all the, so this one has 0 gold. This one has 1 gold. And all the ones that have 1 gold are essentially equivalent to this one. So they're counted there. And then how do the ones have that, how are the ones that have 2 gold beads in them? Well, you can have them next to each other. So I try to draw the beads as a regular hexagon, or you could have them, oh, sorry. One here, and then the blues go like this. Or it could be diametrically opposite. Okay. And I think that pretty much these are all that have 2 golds. And then how about the ones that have 3 golds? So you can have the 3 golds consecutive. Or this way. Or in steps of 2. So these are the ones that have 3 gold. And then by a complementary argument, you can do the ones that have 4, 5, and 6. So let me do the let me do them here. So not this one. one has 4. This one also has 4. And there's one more. So you can see that you can actually pair them up with the ones that have 2 gold in a complementary fashion. And then let's draw the one that has 5 gold. That's the only one. And the last one, the one that has all 6 gold. So if you count them, how many do we get here? So it looks like there are 13 in this situation. So that's clearly not a method that you want to use for larger numbers. So how do you solve this using Burnside Lemma? So what is a group? So clearly the group here is going to be G will be integers mod n, the n, acts on a set X, which consists of all these n tuples, A0, A1, An minus 1, which have the property that A0, A1, An minus 1 come from a set 1, 2, 3 up to lambda. So this is a set of colorings. What is the action? So this is as we define it in the first lecture. 1 acting, so Zn is, let's say, 0 hat, 1 hat, and minus 1 hat, acting on A0, A1, An minus 1, and shifts it to the right. So this is An minus 1, A0, An minus 2, and similarly 2 acting, shifts it to the right by 2, An minus 2, An minus 1. And here we get An minus 3 at the end, and so on. Okay. And now when we are asking the number of colorings, well, the number of necklaces in this case, it can be interpreted as this kind of, I mean, each of these A0, A1, and minus 1, you can interpret them as choices for the beads or for their colors. It's the same thing as the number of orbits of this action, which is 1 over the cardinality of the group overall in G, the fix of G. Okay. So what is this cardinality of Exergy? So let's do some simple examples to figure out. So cardinality of G is clearly n, and now what do we have here? So in we're looking for fix of R. You know, are all the consists of all the sets A0, A, and minus 1 with the property that AJ equals AJ plus R for every J in Zn. So here we do the additions modulo n. Okay. So that's basically how this works. And so how can we calculate this? So this is a cardinality. Okay. So if we had the example when n equals 6, and let's say R equals 2, we had here, we basically have 0, 1, 2, 3, 4, 5. And what do we have? The choice that we have for 0, A0 has to be equal to A2 and has to be equal to A4. And 1 has to be equal to this one, has to be equal to this one. So in this situation, you see that we get the number of such sets is going to be lambda to the power 2, because you can pick the black and the blue, each of them in lambda ways. Okay. So now, what's going to happen in general? Well, what will happen here is that in general, for an arbitrary n and r, if we look, for example, if we look at D, which is, so the subgroup generated by R, so all the multiples of R, this is a subgroup of Zn, and the order of R, which is, it's the cardinality of this subgroup, and the order of R is going to give us the following fact, that the cardinality of fix of R is going to be lambda to the n divided by the order of R. Okay, so in this case here, R was 2, the order of R is 3, and so you see we have this partition into cosets of this subgroup, and each coset has cardinality 3, but there are no, I made a mistake here. No, that's fine. And so we get lambda square such choices. So in general, we're going to get lambda to the n over OR. And now, how do we calculate these orders? Well, the order of an element has to divide the so the order R has to divide n, has to be a divisor of n, and by Lagrange theorem. And if you fix the order, you know, if we have D, so for D dividing n, the number of elements of order D equals phi of D, the Euler's indicator function. So when we put these things together, what we end up with is that the number of colorings, the number of necklaces, will end up being 1 over n, which is the cardinality of the group, summation over all divisors of n d of phi of d times lambda to the power n over d. So that's the number of necklaces which are invariant under circular symmetry.